Building Resilient Systems, a comprehensive guide to the Saga design pattern. Chapter 1, The World of Distributed Systems and Its Challenges. In the ever-accelerating landscape of modern software, the way we build applications has undergone a profound transformation. Just 2 decades ago, a single, all-encompassing software application, a monolith, was the norm. This monolithic design meant that all functionalities, from user authentication to product inventory management, were bundled into a single unit. While simple to deploy initially, these systems often became unwieldy, difficult to scale, and slow to evolve as they grew. Today, the pendulum has swung decisively towards distributed systems. Architectures like microservices, serverless functions, and cloud-native applications break down large, complex systems into smaller, independent, and interconnected services. This fundamental shift wasn't driven by architectural aesthetics. It was a response to pressing business demands for greater agility, resilience, and scalability. But why exactly have organizations moved away from the perceived simplicity of the monolith? Why distributed systems? The motivations for embracing distributed architectures are compelling and address core challenges faced by modern enterprises. Scalability. Imagine an online retail giant preparing for a massive sales event. With a monolithic application, scaling the entire system to handle a sudden surge in traffic is like trying to lift a skyscraper with a single crane. In a distributed system, individual services, say the product catalog service or the payment processing service, can be scaled independently. If only the payment service is under heavy load, you can add more instances of that specific service without having to duplicate the entire application. This targeted scalability allows for highly efficient resource utilization and enables systems to handle enormous user loads. Resilience and fault isolation. A monolithic application operates on an all-or-nothing principle. If a critical component fails, the entire application can crash, leading to a complete outage. In a distributed system, services are isolated from one another. If the recommendation engine experiences an issue, the core e-commerce functionality, like adding items to a cart or completing checkout, can continue uninterrupted. This fault isolation significantly enhances overall system resilience, much like bulkheads in a ship prevent a breach in one compartment from sinking the entire vessel. Independent development and deployment. Large organizations with numerous development teams often find monoliths to be bottlenecks. Every team might be working on different parts of the same codebase, leading to complex merge conflicts, lengthy testing cycles, and infrequent deployment releases. Distributed systems allow teams to own, develop, and deploy their services independently. This autonomy accelerates development cycles, fosters innovation, and enables organizations to deliver new features rapidly and continuously. Technology heterogeneity. A monolithic application typically dictates a single technology stack, one programming language, one database type. This can be restrictive. In a distributed architecture, teams have the freedom to choose the best-fit technology for each specific service. A service handling high-volume real-time analytics might use a specialized NoSQL database, while a service managing financial transactions might stick with a relational database, all within the same overarching system. This flexibility allows for optimized performance and leverages specialized tools. The inherent complexities. While the benefits of distributed systems are undeniable, they introduce a new set of complexities that demand careful architectural consideration. The shift isn't just about breaking apart a big application. It ushers in a fundamentally different set of engineering challenges. Network unreliability. In a monolith, communication between components is direct and immediate. In a distributed system, services communicate over a network. The internet, or even a local area network, is not a perfect medium. Messages can be lost, delayed, or arrive out of order. Services can become temporarily unreachable. Architects must assume the network is unreliable and design systems to cope with these realities rather than assuming perfect connectivity. Partial failures. This is perhaps the most insidious complexity. Unlike a monolith that either works or doesn't, a distributed system can experience individual components failing while others continue to operate. This leads to intricate failure scenarios where one part of a business process might succeed, while another silently fails, leaving the overall system in an inconsistent or indeterminate state. Diagnosing these partial failures is far more complex than debugging a single application crash. Data consistency across service boundaries. This is the crux of the problem the Saga pattern addresses. When data is fragmented across multiple, independent services, ensuring that a single business operation, which might span several services, maintains a consistent view of that data becomes a monumental challenge. For instance, if an online order affects inventory in one service and accounts in another, how do you guarantee that both services always reflect a true and accurate state, especially if one of them fails mid-process? Observability. In a monolithic application, debugging a problem usually involves examining a single log file or debugging a single process. In a distributed system, a single user request might traverse an intricate web of dozens of services, each generating its own logs and metrics. Understanding the end-to-end flow of requests, identifying bottlenecks, or pinpointing the source of an error in such an environment requires sophisticated tooling for distributed tracing, centralized logging, and comprehensive monitoring. Operational overhead. While independent deployments can accelerate development, managing a large number of independent services introduces its own operational burden. Deploying, monitoring, scaling, updating, and debugging. A distributed system requires more sophisticated infrastructure, automation, and operational expertise than a single monolithic application. The need for robust transaction management. Let's consider a common online business process, placing an order. When a customer clicks Buy Now on an e-commerce website, this seemingly simple action triggers a cascade of underlying operations involving multiple services. The order service records that a new order has been placed and moves it to a pending state. The payment service processes the customer's payment. The inventory service deducts the purchased items from stock. The shipping service initiates the delivery process. Ideally, all these steps succeed perfectly. However, what if the payment fails because the customer has insufficient funds? Or what if, after the payment goes through, the inventory system discovers the item is actually out of stock? In a traditional monolithic application, these operations might have occurred within a single, atomic database transaction. If any part failed, the entire transaction would simply roll back to its original state as if nothing ever happened. This is the ACID, guarantee, atomicity, consistency, isolation, durability that traditional databases provide. But in a distributed microservices environment, the payment service, inventory service, and order service each own their own independent databases. There is no single global database transaction that can magically roll back changes across all of them if something goes wrong. If payment succeeds, but inventory fails, you now have a problem. The customer has been charged, but they won't receive the product. This constitutes a severe inconsistency in the system. How do you undo the payment or credit the customer's account in a reliable way without any global rollback mechanism? This challenge of coordinating multi-step business processes across independent services to ensure a consistent outcome, even in the face of partial failures and network unreliability, is precisely the problem the Saga design pattern was created to solve. Conclusion: distributed systems, particularly those built on microservices, offer unparalleled benefits in terms of scalability, resilience, and agility. Yet, they come at the cost of significantly increased complexity, especially when it comes to maintaining data consistency across independent service boundaries. Traditional approaches to transaction management, designed for single database environments, simply cannot meet the demands of modern distributed architectures. This foundational understanding of the why and the what of distributed systems sets the stage for our deep dive into the Saga pattern, a powerful architectural solution specifically crafted to navigate these challenges and enable resilient, consistent business processes in a distributed world. Chapter 2: The Problem of Distributed Transactions, Beyond ACID. In the previous chapter, we established that distributed systems offer immense benefits but introduce significant complexities. particularly regarding data consistency across independent services. We touched upon the concept of atomic transactions and the challenge of coordinating them when data is fragmented. To truly appreciate the elegance and necessity of the Saga pattern, we must first understand why the traditional approach to transaction management falls short in this new distributed paradigm. Review of acid properties. For decades, the gold standard for reliable data management within databases has been the set of properties known as acid. Atomicity. An atomic transaction is an indivisible unit of work. It either completely succeeds, commits, or completely fails, rolls back. There are no partial updates. If a bank transfer involves deducting funds from account A and adding them to account B, atomicity ensures that either both operations happen or neither does. Consistency. A transaction brings the database from one valid state to another valid state. It ensures that all data integrity rules, e.g., uniqueness constraints, foreign key relationships, are maintained. For example, if a bank transfer happens, the total sum of money in all accounts remains consistent. Isolation. Concurrent transactions do not interfere with each other. Each transaction appears to execute in isolation, as if it were the only operation happening on the database. This prevents dirty reads, non-repeatable reads, and phantom reads, ensuring the integrity of data even under heavy load. Durability. Once a transaction has been committed, its changes are permanent and survive any subsequent system failures, e.g., power outages, crashes. Committed data is written to stable storage. These acid properties are incredibly powerful and have served as the bedrock of reliable business applications for decades. For operations confined within a single database, they are effective and provide strong guarantees. Why traditional distributed transactions fall short. The challenge arises when a single business operation cannot be contained within one database. Imagine the user of a modern cloud-native e-commerce site trying to place an order. This single user action likely involves an order service with its own database handling the order details, a payment service with its own database potentially interacting with external payment gateways handling financial transactions, an inventory service with its own database managing stock levels. Now, how do you ensure that the entire business process, order creation, payment, and inventory deduction, either fully succeeds or fully fails, even though each part resides in a different system? Historically, the answer to this problem was a mechanism often referred to as two-phase commit 2PC, sometimes implemented via XA transactions, extended architecture. Two-phase commit 2PC. A closer look. 2PC is a protocol designed to achieve atomicity across multiple participants, e.g., different databases or resource managers. It involves a coordinator or transaction manager and several participants. Phase 1, prepare phase. The coordinator sends a prepare message to all participants asking them if they are ready to commit the transaction. Each participant attempts to prepare its part of the transaction, e.g., by writing changes to a temporary log, acquiring necessary locks. If a participant can successfully prepare, it responds yes to the coordinator. If it cannot, it responds no or simply fails. Phase 2, commit phase or rollback phase. If all participants responded yes, the coordinator sends a commit message to all participants. Each participant then makes its changes permanent. If any participant responded no or failed to respond, the coordinator sends a rollback message to all participants. Each participant then undoes any prepared changes. Limitations of 2PC in modern distributed systems / microservices. While 2PC provides global ACID guarantees, its mechanisms clash severely with the design philosophies of modern distributed systems, particularly microservices. Synchronous and blocking. During the prepare phase, participating services and their underlying resources, e.g., database rows, are often locked for the entire duration of the transaction. This means they are unavailable to other processes until the 2PC completes. This synchronous, blocking nature leads to poor scalability. As the number of participants or the transaction duration increases, resource contention and locking become severe bottlenecks, drastically limiting throughput. High latency. The sequential nature of the two phases introduces significant network overhead and delays, making response times unpredictable and often slow. Tight coupling. All participants must agree on the outcome, and they are tightly coupled to the central coordinator. This contradicts the microservices principle of independent deployability and autonomy. Changes to one service might necessitate coordinating and redeploying other services involved in the 2PC. Single point of failure, conceptual. If the coordinator fails after some participants have prepared, but before the commit rollback decision is finalized, participants can be left in an indeterminate state, holding locks indefinitely. While robust 2PC implementations exist to mitigate this, it introduces significant operational complexity and management of distributed state. Database heterogeneity. 2PC assumes that all participating data stores speak the same transactional language, e.g., all supporting the XA standard. In a microservices architecture, where services are free to choose the best-suited database technology, e.g., MySQL for one, MongoDB for another, a managed cloud service for a third, implementing 2PC across such diverse technologies becomes exceedingly difficult, if not impossible. Furthermore, external services that are not within your control, such as a third-party payment gateway or a shipping carrier's API, will certainly not participate in your internal 2PC. The CAP theorem, brief context. To understand why a different approach is necessary, it's helpful to briefly consider the CAP theorem. This fundamental principle of distributed systems states that a distributed data store can only guarantee 2 out of 3 properties simultaneously. Consistency, all clients see the same data at the same time, regardless of which node they connect to. Availability, every request receives a response, even if some nodes are down. Partition tolerance. The system continues to operate despite network failures, partitions, that prevent some nodes from communicating with others. In the context of highly available, internet-facing microservices, partition tolerance is a non-negotiable requirement. Network failures are inevitable. This means that when a network partition occurs, you must choose between consistency and availability. Most modern distributed systems, prioritizing user experience and uptime, choose availability. This decision implies that strong, immediate consistency, like that provided by ACID and 2PC, must often be sacrificed for eventual consistency. The consistency dilemma. Embracing eventual consistency. Eventual consistency means that while not every transaction is immediately consistent across all services, the system is guaranteed to reach a consistent state eventually, typically within a short period. During the transition, different parts of the system might observe temporary inconsistencies. For many business operations, eventual consistency is perfectly acceptable. If you book a flight, it's okay if a loyalty points update takes a few seconds to propagate, as long as it eventually happens. What's not acceptable is being charged for a flight that wasn't booked, or booking a flight and not being charged. This is where the paradigm shifts. Instead of trying to achieve global ACID transactions that block and couple services, we need a mechanism that allows local transactions within each service to maintain their ACID properties, coordinates these local transactions asynchronously across services, provides a way to undo operations if a later step fails, thereby achieving global business-level consistency, even if it passes through transient inconsistent states. This new approach avoids the problems of 2PC by not locking resources across services and by embracing the realities of network unreliability and partition tolerance. Conclusion: traditional distributed transaction mechanisms like two-phase commit, while offering strong consistency guarantees, introduce significant scalability, availability, and coupling problems in modern microservices architectures. The natural choice for highly available and partition-tolerant systems is to favor eventual consistency. This necessitates a new architectural pattern capable of managing complex, multi-service business processes without resorting to global locks. A pattern that understands the need for undoing actions at a business level. This sets the stage for the Saga pattern, a powerful solution designed precisely for this distributed future. Chapter 3. Introducing the Saga pattern, a new paradigm for consistency. Having explored the limitations of traditional distributed transactions in the context of modern microservices, we now arrive at the core solution, the Saga pattern. This chapter will introduce its fundamental concepts, explain how it achieves consistency in a distributed environment, and provide a clear example to solidify your understanding. The core idea: a sequence of local transactions with compensation. At its heart, the Saga pattern is a way to manage distributed transactions by breaking them down into a sequence of local transactions. Each local transaction operates within a single service's ACID, atomicity, consistency, isolation, durability boundary. This means that within a microservice, you still use your database's traditional ACID transactions to ensure data integrity for operations specific to that service. The critical insight of the Saga pattern is this: if any of these local transactions fails during the multi-step business process, a compensating transaction is executed to undo the effects of all previously completed local transactions. This ensures that the entire business process either completely succeeds or is cleanly reversed, returning the system to a consistent state. Think of it like this: a normal ACID transaction is an all-or-nothing operation. If one part fails, the whole thing rolls back technically from the database's perspective. A Saga, on the other hand, is still all or nothing from a business perspective, but it achieves this by running forward through steps, and then, if necessary, running backward through a series of new business operations that compensate for the forward steps that have already occurred. Analogy: the travel agent's dilemma. Imagine a customer asks a travel agent to book a complex trip involving a flight, a hotel, and a car rental. Book flight. The agent first books the flight. This is a local transaction, committing the flight reservation in the airline system. Book hotel. Then, the agent books the hotel, another local transaction, committing the hotel reservation in the hotel system. Book car rental. Finally, the agent tries to book the car rental. But wait, all cars are booked. In a traditional ACID world, the entire flight hotel car transaction would ideally roll back. But our travel agent has already committed the flight and hotel reservations. They can't simply magically unbook them as if they never happened. Instead, the agent performs compensating actions. Cancel hotel. The agent calls the hotel to cancel the reservation. Cancel flight. The agent calls the airline to cancel the flight. Through this sequence of forward steps, and if necessary, backward compensating steps, the travel agent ensures that the booking a trip business process either completely succeeds, all booked, or completely fails, and is reliably undone, all canceled. Even though each individual booking was a separate, committed local transaction. This is the essence of a Saga. Local transactions, the building blocks. Within a Saga, each participating service executes its part of the business process as a distinct local ACID transaction. For example, the payment service ensures that when it processes a payment, the debit from the customer's account and the credit to the merchant's account are an ACID transaction within its own database. The inventory service ensures that when it deducts an item from stock, the stock count update is an ACID transaction within its database. These local transactions are atomic and consistent within their own service boundaries. The Saga pattern then coordinates these independent local transactions. Compensation transactions, the undo but compensating transactions, are the cornerstone of the Saga pattern's ability to maintain consistency. A compensating transaction is a business operation that semantically reverses the effects of a previously executed local transaction. It's crucial to understand that it's not a technical database rollback to a prior state. It's a new action taken to negate the business impact of a previous action. Why it's critical? Because services commit their local transactions immediately, a traditional rollback is impossible once a service has made changes public. Compensation provides the necessary undo button for distributed business processes. Examples of compensating actions: original action, charge customer account; compensation, refund customer account; original action, deduct inventory; compensation, restore inventory or increase inventory; original action, create order in order service; compensation, cancel order in order service; original action, send confirmation email; Compensation. Send cancellation email. Designing compensating actions requires careful thought. What if the compensation itself fails? What if the original action had external side effects that are hard to undo? These are important considerations for robust Saga design, which we'll cover in Chapter 5. Key principles of the Saga pattern. Eventual consistency. The system temporarily enters an inconsistent state during the Saga's execution. For instance, payment might be processed before inventory is confirmed. However, the Saga guarantees that the system will eventually reach a final consistent state, either with the entire business process successfully completed or fully compensated. This embraces the reality of distributed systems rather than fighting against it. No global locks. Unlike 2PC, Sagas do not involve holding locks across multiple services. Each service performs its local transaction and releases its resources immediately. This significantly improves availability and scalability. Asynchronous communication. Sagas heavily rely on asynchronous messages or events to coordinate steps between services. A service completes its work, publishes an event, and then other services react to that event. This asynchronous nature further enhances decoupling and scalability. Historical context. Though seemingly a modern solution tailored for microservices, the Saga pattern is not new. It was first articulated in a 1987 paper titled Sagas by Hector Garcia Molina and Kenneth Salem. Their insights, conceived pre-internet and certainly pre-microservices, proved remarkably prescient. The rise of microservices, with their independent data stores and emphasis on loose coupling, brought the Saga pattern back into prominence as designers grappled with distributed consistency challenges. Walkthrough example. Simplified e-commerce order processing. Let's illustrate a typical e-commerce order process using a Saga: the business process, happy path, order service. Customer places an order. The order service records the order in a pending state in its database, local transaction 1. It then publishes an order-created event. Payment service. The payment service consumes the order-created event. It processes the payment with a payment gateway. If successful, it updates its internal records, local transaction 2, and publishes a payment processed event. Inventory service. The inventory service consumes the payment processed event. It deducts the items from stock. If successful, it updates its internal records, local transaction 3, and publishes an inventory deducted event. Shipping service. The shipping service consumes the inventory deducted event. It schedules the shipment. If successful, it updates its internal records, local transaction 4, and publishes a shipment scheduled event. Order service, final step. The order service consumes the shipment scheduled event. It updates the order status to completed in its database, local transaction 5. The business process, failure path, payment fails. Now let's consider a failure. Imagine step 2, payment processing, fails due to insufficient funds. Order service, customer places an order. Order service records order as pending TL1, publishes order created. Payment service, consumes order created, attempts payment. Payment fails. It records the failure, TL2, and publishes a payment failed event. Order service, compensation TL1, the order service consumes the payment failed event. It then performs a compensating transaction for TL1. It updates the order status from pending to canceled in its database. In this scenario, the Saga successfully reversed the business intent. The order was canceled, and the system is in a consistent state relative to this order. No items were deducted from inventory, and no shipment was scheduled. The business process, failure path, inventory fails. What if payment succeeds but inventory deduction fails? Order service, order pending, TL1. Publishes order created. Payment service, payment succeeds, TL2, publishes payment processed. Inventory service, consumes payment processed, tries to deduct items. Inventory deduction fails, e.g., item out of stock. It records this failure, TL3, and publishes an inventory deduction failed event. Payment service, compensation, TL2. The payment service consumes inventory deduction failed. It performs a compensating transaction for TL2. It refunds the customer. It publishes a payment refunded event. Order service, compensation TL1, the order service consumes payment refunded. It performs a compensating transaction for TL1. It updates the order status from pending to canceled. Here, the Saga ensures that even though payment occurred, the system recovers by issuing a refund and canceling the order, bringing it back to a consistent state. Conclusion: the Saga pattern provides a pragmatic and powerful solution for managing distributed business processes. By decomposing complex workflows into a series of local, ACID-guaranteed transactions and leveraging compensating actions for rollback, Sagas embrace the realities of eventual consistency. This approach delivers resilient, scalable multi-service operations without the pitfalls of traditional distributed transactions, making it an indispensable pattern for modern distributed system design. Chapter 4. Types of Sagas: Choreography versus Orchestration. In the previous chapter, we introduced the fundamental concept of a Saga, a sequence of local transactions with compensatory actions. While the core idea remains constant, Sagas can be implemented using two distinct architectural styles: choreography and orchestration. Each approach has its own characteristics, trade-offs, and suitability for different business complexities. Choosing between them is a critical design decision. Introduction: two approaches to coordination. Imagine a group of people performing a synchronized dance. In a choreographed performance, there's no single leader dictating every step. Each dancer knows their part and reacts to the movements of their fellow dancers, triggering their next move based on cues. In an orchestrated performance, a conductor stands at the front, leading the entire ensemble. The musicians look to the conductor for cues, and the conductor ensures everyone plays their part at the right time. These two analogies perfectly capture the essence of Saga choreography and orchestration. Choreography Saga: the decentralized dance. Concept: in a choreography Saga, there is no central orchestrator. Instead, each service involved in the Saga performs its local transaction and then publishes an event. Other services listen to these events and react accordingly by initiating their own local transactions, potentially publishing new events. The overall business process emerges from this chain of interconnected, event-driven interactions. Every service essentially acts as a dancer, reacting to the dance moves, events of others. How it works: Service A completes its local transaction and publishes event A. Service B consumes event A, performs its local transaction, and publishes event B. Service C consumes event B, performs its local transaction, and publishes event C, and so on. If any service fails its local transaction, it might publish a failed event, which other services would then consume to trigger their compensating transactions. Example scenario: simple order processing, choreography. Let's revisit our e-commerce order process. User creates an order. Order service initiates a local transaction, LT1, to create the order in pending status. Order service publishes an order-created event to a message broker. Payment service listens for order-created events. It processes the payment, LT2, and publishes either payment processed or payment failed. Inventory service listens for payment processed events. It deducts stock, LT3, and publishes either inventory deducted or inventory deduction failed. Shipping service listens for inventory deducted events. It schedules shipment, LT4, and publishes shipment scheduled. Order service also listens for payment failed or inventory deduction failed events. If it receives one, it triggers a compensating transaction, CT1, to cancel the order. Payment service also listens for inventory deduction failed events. If it receives one, it triggers a compensating transaction, CT2, to refund the payment. Pros of choreography Sagas: high decoupling. Services are highly independent. They only need to know about the events they produce and consume. There is no central point of coordination that services need to be aware of, minimizing direct dependencies. Simplicity for small Sagas. For straightforward, linear workflows with few steps, choreography can be faster to implement initially, as you don't need to build and maintain a separate orchestrator component. Less single point of failure risk, conceptually. Logic is distributed across services, so the failure of one service doesn't necessarily halt the entire Saga, assuming message brokers are resilient. Cons of choreography sagas: distributed logic, hard to trace, the biggest drawback. The overall business logic for the saga is implicitly defined by the chain of events and listeners scattered across multiple services. It's difficult to get an overview of the end-to-end flow, making debugging, monitoring, and understanding the saga's state challenging. This is often referred to as distributed spaghetti. Potential for cyclic dependencies. In complex scenarios, it's easy to inadvertently create circular dependencies between services through their event subscriptions. Difficult to evolve. Modifying the saga's flow often requires touching multiple services simultaneously to change their event publishing consumption logic, reducing agility. Absence of events. What if a service silently fails to publish an expected event? The saga might get stuck indefinitely without a clear recovery path. Timeouts are harder to manage centrally. Orchestration saga. The centralized conductor. Concept. In an orchestration saga, a dedicated component, the saga orchestrator, also known as a saga coordinator or controller, manages the entire workflow. The orchestrator is responsible for sending commands to participant services, waiting for their responses or events, and then deciding the next step. It explicitly controls the flow of the saga, including initiating compensating transactions if a step fails. How it works: the orchestrator receives a request to start a saga. It sends a command to service A performs its local transaction and sends a reply, e.g., an event indicating success or failure, back to the orchestrator. Based on service A's reply, the orchestrator decides whether to send a command to service B for the next step, or to service A's compensating transaction, or another service's compensating transaction. The orchestrator maintains the state of the saga throughout its execution. Example scenario: order processing orchestration. User creates an order. A request reaches the order service, which starts an order Saga orchestrator instance. The order Saga orchestrator records the initial state and sends a process payment command to the payment service. Payment service processes payment, LT2, and sends back a payment processed event or payment failed event. If payment processed event, order Saga orchestrator sends a deduct inventory command to the inventory service. Inventory service deducts stock, LT3, and sends back inventory deducted event or inventory deduction failed event. If inventory deducted event, order Saga orchestrator sends a schedule shipment command to the shipping service. Shipping service schedules shipment, LT4, and sends back shipment scheduled event. If shipment scheduled event, order Saga orchestrator updates the order status to completed in the order service, LT5. If payment failed event or inventory deduction failed event, order Saga orchestrator initiates compensation. If payment failed event, it directly updates the order to canceled, LT1 compensation. If inventory deduction failed event, it sends a refund payment command to payment service, LT2 compensation, and updates the order to canceled, LT1 compensation. Pros of orchestration sagas: clear flow and centralized logic. The entire business process is explicitly defined within the orchestrator. This makes it far easier to understand, design, debug, and monitor the end-to-end flow. The orchestrator effectively manages the saga's state as a state machine. Easier to monitor and debug. The orchestrator's state provides a clear snapshot of where the saga is in its execution, what steps have completed, and what needs to happen next. Robust error handling. The orchestrator is explicitly designed to handle various outcomes, success, failure, timeout, and trigger precise compensation logic, offering more granular control. Easier to evolve. Changes to the saga flow primarily involve modifying the orchestrator, potentially reducing the need to modify multiple participant services simultaneously. Cons of orchestration sagas: orchestrator complexity. The orchestrator itself can become complex, especially for very large sagas with many steps, branching logic, and diverse failure scenarios. It needs to manage state, timeouts, retries, and different execution paths. Potential bottleneck SBOF, conceptual risk. A poorly designed or implemented orchestrator could theoretically become a bottleneck or a single point of failure if not built with scalability and resilience in mind. However, most modern orchestrators are built to be highly available and durable. Coupling to orchestrator. Participant services become implicitly coupled to the orchestrator. They respond to its commands events, though they remain loosely coupled to each other. Choosing between choreography and orchestration. The decision between choreography and orchestration is a classic trade-off in distributed system design. There's no one-size-fits-all answer. The optimal choice depends on several factors. Complexity of the saga, choreography, best suited for simpler, linear sagas with few steps, where the flow rarely changes and the number of participating services is small. Orchestration, preferred for complex sagas with many steps, branching logic, e.g., if-then-else conditions based on outcomes, various outcomes, and where clear visibility, robust error handling, and easier evolution are crucial. Decoupling versus centralized control, choreography, maximizes decoupling, but the business logic is dispersed and harder to infer. Orchestration introduces a degree of centralized control, which facilitates understanding and management but slightly increases coupling to the orchestrator. Team structure and communication. If teams are truly independent and communication overhead needs to be minimized, choreography might seem appealing, but the implicit dependencies can become communication hurdles down the line. If teams can easily coordinate on a shared saga definition, even if implemented within separate services, orchestration often leads to more maintainable and understandable systems. Observability requirements. If you need a clear, single point to monitor the progress of a saga, handle timeouts, and debug failures, orchestration is generally superior. Conclusion. Both choreography and orchestration are valid and effective ways to implement the saga pattern. Choreography promotes maximum decoupling and can be initially simpler for very basic workflows, but its lack of centralized state and distributed logic can quickly become a maintenance and debugging nightmare for anything beyond trivial scenarios. Orchestration provides much-needed visibility, control, and explicit error handling, making it the preferred choice for most real-world complex business processes that span multiple services. The discerning architect understands these trade-offs and selects the style that best aligns with the specific requirements of the business domain, the complexity of the saga, and the operational needs of the system. Chapter 5. Designing Effective Sagas, Compensation, Idempotency, and Atomicity. Understanding the fundamental concept of a saga and its two primary implementation styles, choreography and orchestration, is merely the beginning. To design truly effective, robust, and reliable sagas, we must dive deeper into critical principles that ensure business consistency, even in the face of pervasive failures. Compensation, idempotency, and achieving atomicity at the business level. These are the cornerstones upon which resilient distributed transactions are built. Compensation logic. The undo for distributed systems. As discussed, compensation is what allows a saga to roll back effects when a local transaction fails or a critical business condition is not met. While the concept is simple, its implementation requires meticulous design. Definition review. A compensating transaction is a business operation that semantically reverses the effects of a previously committed local transaction. It's crucial to distinguish this from a technical database rollback. Once a local transaction commits within its service's database, its changes are durable. Compensation is a new action taken by the system to nullify the business impact of that prior action. Why it's critical. In a distributed system, you cannot perform a global, technical rollback across independent services. Each service makes its changes, commits them to its own database, and often communicates these changes to external systems or users. Compensation is the only reliable way to bring the system back to a valid, consistent state from a business perspective. Designing compensable operations. Every confirmed step needs a counterpart. For every local transaction that commits within a saga, you must have a defined compensating action. If a step cannot be compensated, e.g., irreversible physical action like sending an email, it's often best placed as the very last step in a saga's successful path, ideally after all other reversible steps are complete. Focus on business effects. Compensation isn't about reverting database bytes, It's about reversing the business effect. If a local transaction charged account X, its compensation should be refund account X. If it deducted inventory for product Y, its compensation should be restore inventory for product Y. If it reserved a seat, its compensation is release seat reservation. Compensation can also fail. A common oversight is assuming compensation will always succeed. What if the compensation itself encounters an error, e.g., the refund gateway is down? Retry mechanisms for compensation. Compensation attempts should ideally be idempotent and designed with aggressive retries, similar to how you'd handle retries for any critical operation. Human intervention paths. For severe or persistent compensation failures, there must be a defined pathway for human intervention. This might involve alerts, manual data cleanup, or human-initiated processes to resolve the inconsistency. The system tries its best, but sometimes a human is needed to rectify complex business states. Idempotency of compensation. Just like forward operations, compensation operations must also be idempotent. You don't want to double refund a customer if a retry mechanism attempts compensation twice. Idempotency, making operations repeatable. If compensation is the undo button, idempotency is the don't screw up if I press the button twice guarantee. Definition: an operation is idempotent if executing it multiple times has the same effect as executing it once. Sending the same request or performing the same action repeatedly does not cause unintended side effects or change the system's state beyond the initial execution. Why it's essential for Sagas. Sagas fundamentally rely on asynchronous message passing, which often operates on an at least once delivery guarantee. This means messages or commands might be duplicated. A message broker might deliver the same message twice. Retried. A service might fail to respond, causing an orchestrator or a sending service to retry sending a command. Network glitches. Temporary network issues might cause a client to resend a request even though the server successfully processed the first one. Without idempotency, these scenarios could lead to catastrophic business inconsistencies. Charging a customer twice for the same order. Deducting inventory twice for a single item. Creating duplicate records. Issuing multiple refunds for a single failed payment. Achieving idempotency. Unique message IDS/correlation IDS. The most common approach. When a service receives a command or event, it checks if it has already processed a message with that specific unique identifier, often stored in a dedicated processed messages table or within the entity itself. If it has, it simply ignores the duplicate or returns the original successful response without reprocessing. Conditional updates. Update a record only if its current state matches an expected value. For example, change order status from pending to processed is idempotent if the target status is processed and the source status is pending. If the status is already processed, the operation does nothing further. Leverage business keys. When performing updates, use natural, unique business identifiers, e.g., orderid, payment transactioned, in your database queries. If you try to create a record with a unique constraint that already exists, the second attempt will naturally fail or be ignored by the database. Deletions are often not idempotent. Deleting an item and then trying to delete it again might result in an error. A more idempotent approach might be to mark as deleted or archive. State machines. For an orchestrator, its internal state machine naturally handles idempotency. If it receives a message that corresponds to a completed or already processed state transition, it simply ignores it or acknowledges without further action. Atomicity at the business level. The Saga pattern redefines atomicity for distributed systems. Instead of technical ACID atomicity across services, it provides business-level atomicity. This means the entire business process, spanning multiple services and their respective local transactions, is guaranteed to reach a final, consistent state from a business perspective. It either fully completes or is fully compensated. Key characteristics of business-level atomicity in Sagas. No global commit rollback. Each service performs and commits its local ACID transaction independently. There is no single, global commit for the entire Saga. The rollback is not a technical database rollback, but a sequence of new business operations, compensations. Embracing eventual consistency. During the execution of a saga, the system will temporarily pass through states that are inconsistent at a global level, e.g., payment processed, but inventory not yet deducted. Business-level atomicity ensures that it will not remain in such a state. It progresses to success or reverts cleanly. The dangling purchase problem. This is a crucial concept to avoid. It refers to a scenario where a saga fails, and its compensation logic also fails or is incomplete, leaving the system in a truly inconsistent state that requires manual intervention. For example, a customer is charged, but the order is never fulfilled and no refund is issued. Good Saga design meticulously plans for all compensation paths, including retries for compensation, to minimize the risk of such dangling states. Designing for visibility and traceability. While not directly about consistency guarantees, designing for visibility and traceability is paramount for managing sagas effectively and ensuring their business atomicity. You need to be able to answer, where is this particular order saga at right now, and why did this saga fail? Correlation IDs, Saga IDs. A unique identifier, e.g., a GUID, must be generated at the very beginning of a saga and passed along with every single message or command related to that saga. Every service involved must propagate and log this ID. This ID allows you to stitch together the entire flow of messages and operations across multiple services, forming a complete picture of the saga's execution. Centralized logging and monitoring. Aggregate logs from all services into a central system. By filtering logs based on the correlation ID, you can instantly see the entire journey of a single saga. Distributed tracing tools, conceptually not prescriptive for this book, can then visually represent these flows, helping to identify bottlenecks or visualize failure points. Saga state reporting, especially for orchestration. If you're using an orchestrator, its internal state machine provides an explicit record of the saga's progress. You can expose this state via an API or dashboard to see which step a saga is on, which steps are pending, and explicitly map failure states. Conclusion: building effective sagas requires a deep understanding and meticulous application of these principles. Compensation actions are your distributed systems, undue functionality, vital for business-level consistency. Idempotency is the shield that protects your system from the perils of message duplication and retries inherent in distributed, asynchronous communication. Finally, embracing business-level atomicity means designing your distributed processes to always reach a valid end state, even if it involves complex compensation chains. By prioritizing these design considerations and ensuring clear visibility, you can leverage sagas to build truly resilient and trustworthy distributed systems. Chapter 6. Implementing sagas, conceptual tools and technologies. With a solid understanding of the saga pattern's principles and design considerations, we now turn our attention to how these concepts are translated into practical implementations. Sagas fundamentally rely on message-driven architectures. This chapter explores the conceptual tools and classes of technologies commonly employed to build sagas, emphasizing foundational principles over specific code. Understanding these underlying mechanisms is crucial, whether you're building a saga from scratch or leveraging a pre-built framework. Message brokers, the central nervous system of sagas. At the core of almost any saga implementation lies a message broker, or message queue. These robust middleware components act as the central nervous system for communication between services in a distributed system. Examples include Apache Kafka, RabbitMQ, ActiveMQ, Azure Service Bus, AWS SQS SNS, and Google Cloud PubSub. Role in sagas. Message brokers provide the asynchronous, decoupled communication fabric necessary for sagas to operate efficiently. Decoupling. Services don't need to know the direct network addresses or availability of other services. They simply send messages to or consume messages from the broker. This breaks direct dependencies and enhances system flexibility. Reliable delivery. Brokers are designed to ensure that messages reach their intended consumers. They offer various delivery guarantees, e.g., At least once delivery is common, meaning a message is delivered at least once, which necessitates idempotency in consumers. Event publishing subscription. For choreography sagas, services publish events, e.g., payment processed, and other services subscribe to these events to react. For orchestration sagas, the orchestrator sends commands, e.g., process payment, and receives responses, e.g., payment processed event. Brokers facilitate both publish-subscribe and point-to-point communication patterns. Durability and persistence. Most brokers persist messages to disk, ensuring that messages are not lost if a service or the broker itself restarts. This is vital for guaranteeing that a saga can progress even after transient failures. Scalability. Message brokers are built to handle high volumes of messages, allowing distributed systems to scale to meet demand without becoming communication bottlenecks. Core broker concepts. Queues, for point-to-point communication, where only one consumer actively processes a message, e.g., an orchestrator sending a command to a specific service. Topics exchanges, for publish-subscribe communication, where a single message published to a topic can be delivered to multiple interested consumers, e.g., a service publishing an event that multiple other services might need to react to. The transactional outbox pattern, for atomic message publishing, one of the most critical challenges in building reliable event-driven and Saga-based systems is ensuring that a change to a service's local database and the publishing of a corresponding event are atomic. In other words, either both happen or neither happens. The problem: consider a service that processes a payment and then needs to publish a payment-processed event. If the service updates its database successfully but crashes before it can send the message to the message broker, you have a crucial inconsistency. The database reflects the payment, but no other service knows about it. The saga is stuck. The solution, conceptual, the transactional outbox pattern. This pattern solves the atomicity problem by leveraging the database's ACID properties. Write to outbox table. Instead of publishing the message directly to the broker, messages are first written to a dedicated outbox table within the same database transaction as the business data change. This means if the business transaction rolls back, the outbox message also rolls back. If the business transaction commits, the outbox message also commits. Separate relayer process. A separate, dedicated process, often called a message relay, outbox polar, or change data capture, CDC mechanism, periodically reads messages from the outbox table. Publish to broker. This relayer process then takes the messages from the outbox table and publishes them reliably to the message broker. Once successfully published, the message in the outbox table is marked as sent or deleted. Importance for sagas. The transactional outbox pattern guarantees that Saga participants reliably emit the events or commands required to progress or compensate the Saga. It prevents lost updates from a distributed perspective and ensures that once a local transaction is committed, its effects are consistently communicated to the rest of the system. Event sourcing, briefly complementary. While not strictly required for sagas, event sourcing is a complementary pattern that naturally aligns with Saga principles. Concept. Instead of storing only the current state of an entity, event sourcing stores the entire sequence of immutable events that have occurred to an entity, e.g., order created, item added, payment initiated, order shipped. The current state is then derived by replaying these events. Saga relationship. Services that are event-sourced are inherently event publishers. Their immutable event log makes it straightforward to publish events to drive a saga. Event sourcing also provides a rich audit trail, which can be invaluable for debugging and understanding the flow of complex sagas. State machines, modeling orchestrator logic. For orchestration sagas, managing the complex flow of commands, events, and compensation logic is best handled using a state machine. Role in orchestration sagas. A saga orchestrator commonly functions as a finite state machine. It has states, well-defined stages of the saga, e.g., order pending payment, payment processed, awaiting inventory, saga compensating. Events inputs, messages received from participant services, e.g., payment processed, inventory deduction failed. Transitions, rules that dictate how the orchestrator moves from one state to another based on incoming events and its internal logic. Actions, commands sent to participant services, e.g., process payment command, refund payment command. Benefits, clarity and explicitness, provides a clear, graphical if visualized, and explicit way to define complex Saga workflows, including all success paths, various failure paths, and the corresponding compensation logic. State management simplifies the orchestrator's internal complexity by providing a structured way to manage the Saga's progress reliably. Auditability. The state changes provide a clear audit trail of the Saga's execution. Conceptual implementation. State machines can be custom-built using simple switch statements or conditional logic, or you can leverage specialized state machine frameworks and libraries available in most programming languages. In serverless environments, cloud-native workflow services like AWS Step Functions or Azure Durable Functions are essentially managed durable state machines, greatly simplifying orchestrator implementation. Frameworks and libraries, conceptual mention. Building Sagas from scratch involves considerable boilerplate for message handling, state management, and error recovery. Recognizing this, many higher-level frameworks and libraries have emerged to simplify Saga implementation. In Java, Axon Framework, Camunda, Activity. In Net, Mass Transit, and Service Bus. Cloud Native. Oz Step Functions, Azure Durable Functions, Google Cloud Workflows. These tools abstract away much of the underlying complexity, providing durable state management, reliable message dispatch, and often visual design tools for workflows. While they streamline development, the core principles discussed in this book remain fundamental to understanding and effectively using them. Illustrative conceptual example, integrated flow. Purchase ticket saga. Let's tie these concepts together with a conceptual purchase ticket saga using orchestration. Start Saga. A client sends a request purchase command. Ticketing service, local transaction and outbox. The ticketing service receives request purchase. It begins a local database transaction, inserts ticket reservation record in pending state, inserts a ticket purchase requested message into its outbox table, commits the local transaction. Outbox relayer, a separate process, the transactional outbox relayer, detects the new message in the ticketing service's outbox table. It publishes the ticket purchase requested event to the message broker. Ticket Saga Orchestrator, State Machine. The Ticket Saga Orchestrator, a durable state machine, consumes the ticket purchase requested event. It updates its internal state to awaiting payment. It sends a process payment command to the payment service via the message broker. It sets a timeout for the payment response. Payment service, local transaction and outbox. The payment service consumes process payment command. It performs its local database transaction, e.g., debits customer account, and interacts with an external payment gateway. If successful, it inserts a payment processed event into its outbox table, marking the command as completed. If failed, it inserts a payment failed event into its outbox table, commits the local transaction. Outbox relayer publishes payment processed or payment failed to the message broker. Ticket Saga Orchestrator, State Machine. If payment processed, updates state to payment confirmed, awaiting ticket issuance, sends issue ticket command to ticketing service. If payment failed, updates state to payment failed, initiating compensation, sends cancel ticket reservation command to ticketing service. This is the compensation for LT1 handled by orchestrator logic. If timeout expires before either receives, update state to payment timed out, initiating compensation, sends cancel ticket reservation command to ticketing service. This iterative process continues, with the orchestrator guiding the Saga through success or compensating paths using messages, relying on the transactional outbox to ensure atomicity of local changes and message emission. Conclusion: implementing Sagas effectively requires leveraging a combination of conceptual building blocks. Robust message brokers provide the asynchronous communication backbone. The transactional outbox pattern guarantees atomic changes within services and reliable event publishing. State machines are invaluable for explicitly modeling complex Saga logic, especially in orchestration. while many frameworks simplify Saga development. Understanding these underlying conceptual tools and their interactions is fundamental to designing, building, and operating resilient distributed systems capable of handling complex business transactions. Chapter 7: Advanced Saga Concepts and Operational Excellence. Designing a Saga that correctly models a distributed business process is a significant achievement. However, true success lies not just in a well-designed architecture, but in its ability to operate reliably, gracefully handle failures, and be effectively managed in a production environment. This chapter delves into advanced Saga concepts and the operational practices vital for building truly resilient distributed systems. Error handling and retries. Navigating the unpredictable. In distributed systems, failures are not exceptions, they are guaranteed occurrences. Networks fail, services crash, databases become unavailable. Effective Saga implementation must proactively address these realities. Transient failures. These are temporary, self-resolving issues, e.g., a brief network glitch, a database momentarily overloaded. Automatic retries with backoff. Implement retry mechanisms for all inter-service communication, commands, event consumption, API calls. A crucial addition is exponential backoff with jitter. This means increasing the delay between retries exponentially, e.g., 1s, 2s, 4s, 8s, and adding a small random jitter to avoid overwhelming a recovering service with synchronized retries from multiple clients. Most message brokers and HTTP client libraries offer configurable retry policies. Circuit breakers. For persistent or non-transient failures, continuous retries can exacerbate the problem, causing cascading failures. A circuit breaker pattern detects when a remote service is consistently failing and trips, preventing further calls to that service for a predefined period. This gives the failing service time to recover and prevents the calling service from wasting resources on doomed requests. Idempotency is key, revisited. All retriable operations must be idempotent to prevent duplicate processing of messages or commands. Non-transient, business, failures. These are failures that won't resolve on their own, often due to business logic or external system constraints, e.g., insufficient funds, item out of stock, invalid customer ID. Explicit compensation logic. This is the primary mechanism discussed in Chapter 5. The Saga's orchestrator, or the individual services in a choreographed Saga, must explicitly define and trigger compensating transactions when such failures occur. Dead letter queues, DLQs. For messages that consistently fail to be processed after all retry attempts, e.g., due to data serialization errors, unhandled exceptions, or a bug in the consumer, they should be moved to a dead letter queue. This prevents poison messages from blocking the main processing queue. Messages in DLQs are typically inspected manually, debugged, and either requeued for processing or discarded. Human intervention. Not all failures can be automatically compensated or resolved. For critical business processes, define clear processes for human alerts. This might involve system administrators, support teams, or domain experts. The system flags the issue, provides all necessary context, Saga ID, error details, and a manual procedure is initiated to inspect, repair data, or manually reinitiate a compensating action. Timeouts and deadlines. Managing long-running processes. Sagas can span seconds, minutes, hours, or even days. Distributed systems are prone to delays or silent failures where a response never arrives. Challenge of long-running Sagas. A service might crash after performing its local transaction, but before sending its response back. A message could get lost permanently, or an external system might simply be slow or unresponsive. Timeout mechanisms. Orchestrator-managed timeouts. In an orchestration Saga, the orchestrator sets a specific deadline for receiving a response from a participant service. If the response isn't received within this timeout, the orchestrator assumes a failure and triggers its defined failure handling and compensation logic. Message TTL, time to live. Message brokers often support message time to live. If a message isn't processed within its TTL, it can expire and automatically be moved to a DLQ or trigger a specific error handling pathway. This helps prevent messages from being indefinitely stuck. Business deadlines. Beyond technical timeouts, some sagas have strict business deadlines. For example, a reservation for concert tickets might only be held for 15 minutes. The saga design must account for these by having separate mechanisms, e.g., scheduled jobs that check for expired reservations and trigger cancellation sagas, to ensure business rules are enforced. Monitoring and observability. Seeing the unseen. Operating distributed systems without robust observability is like navigating a maze blindfolded. For sagas, this is even more critical due to their multi-service, asynchronous nature. Tracing saga execution. Correlation IDs. As previously discussed, a unique saga ID, also known as trace ID or correlation ID, must be propagated with every single message, command, and log entry related to a specific saga instance. This is the single most important tool for debugging and monitoring sagas. Distributed tracing tools. Implement conceptual distributed tracing to visualize the end-to-end flow of a single request or message chain across all involved services. Tools like Jaeger, Zipkin, or OpenTelemetry, integrating with APM solutions, conceptually allow you to see the waterfall of events and processing duration for an entire saga, helping to pinpoint where bottlenecks or failures occurred. Logging. Implement comprehensive, structured logging in each service. Logs should include the Saga ID correlation ID, the type of message event being processed, the outcome of the processing, success, specific error, relevant business context, e.g., order ID, customer ID. Metrics. Collect and monitor key performance indicators, KPIs for your sagas, saga completion rates. Track the percentage of sagas that complete successfully versus those that enter a compensated or failed state. Saga duration. Monitor the average, median, and P99, 99th percentile, latency for sagas to complete. Spikes can indicate performance bottlenecks. Compensation rates. Track how often compensation paths are triggered. A high rate might indicate underlying issues in upstream systems or faulty business logic. Message broker metrics. Monitor queue depths, message processing rates, consumer lag, and DLQ sizes to identify communication bottlenecks or processing issues. Dashboards and alerts. Create clear dashboards that visualize the health of your sagas. Set up proactive alerts for decreased saga success rates, increased saga duration, growing DLQ sizes, high rates of specific compensation events, testing sagas. Beyond the happy paths, testing distributed systems is inherently challenging, and sagas add another layer of complexity. Rigorous testing, especially of failure and compensation paths, is paramount. Unit tests. Test individual components within each service, including their local transaction logic and how they interpret messages. Integration tests. Test the interaction between two services and the message broker, e.g., Service A publishes an event, Service B consumes it correctly. Saga-specific integration tests. Orchestration sagas. Test the orchestrator's state machine transitions exhaustively. Provide various responses from mock participant services, success, specific failures, timeouts, to ensure the orchestrator navigates to the correct state and triggers appropriate commands or compensations. Choreography sagas. Testing choreography is harder because it lacks a central control point. You typically test sequences of events, ensuring that the expected chain of reactions occurs across services. This often involves setting up test environments that mimic the message broker interactions. End-to-end, E2E tests. These are the most valuable but also the most complex. Simulate a full saga execution across all services, including injecting failures at various points to verify that compensation paths are correctly triggered and executed. This often requires sophisticated test harnesses, potentially in dedicated test environments. Testing compensation paths. This cannot be stressed enough. The undo logic is often more complex and critical than the happy path. Test every possible failure scenario and ensure the system correctly compensates and restores a consistent state. Chaos engineering brief mention. For mature distributed systems, consider introducing controlled intentional failures, e.g., network latency, service instance crashes, database failures, in a production or pre-production environment. This chaos engineering helps uncover weaknesses in your Saga design and operational resilience before they cause real problems. Version control for Sagas. Long-running Sagas pose unique challenges when evolving your system. What happens if a Saga starts with version 1 of your services, but halfway through, you deploy version 2 with modified logic? Backward compatibility. Design your service APIs and message schemas to be backward compatible for existing, in-flight Sagas. New Saga versions. For significant changes, new Sagas might be initiated with the new version of the logic, while existing Sagas are allowed to complete using the older logic. Migration strategies. For very long-running Sagas, you might need to design explicit migration strategies to move an ongoing Saga to a new logic version, if absolutely necessary. Conclusion. Operating Sagas effectively in a production environment demands a robust operational strategy. Moving beyond the theoretical design, it requires a meticulous approach to error handling, building in comprehensive retry and timeout mechanisms, and investing heavily in observability through consistent logging, correlation IDS, tracing, and metrics. Furthermore, rigorous testing, especially for all unhappy paths and compensation flows, is non-negotiable. By prioritizing these operational considerations, organizations can build truly resilient distributed systems that not only function correctly, but also recover gracefully from the inevitable failures of the distributed world. Chapter 8, Real-World Saga Case Studies. The previous chapters laid the theoretical groundwork for understanding the Saga pattern, its types, and core design principles. Now, let's bring these concepts to life with real-world case studies. By examining concrete scenarios across various industries, we can better appreciate why the Saga pattern is chosen, where it excels, and the practical challenges and lessons learned in its application. These examples highlight the pattern's versatility and its indispensable role in solving complex distributed transaction problems. Case Study 1, E-commerce order fulfillment. Scenario: a customer places an order on an e-commerce website. This initiates a multi-step process: order creation, payment processing, inventory deduction, and shipping scheduling. The distributed problem. In a microservices architecture, these functions are typically handled by separate services, e.g., order service, payment service, inventory service, shipping service, each with its own database. A traditional ACID transaction cannot span these independent services and an external payment gateway. If payment fails after inventory is deducted, the system becomes inconsistent. The item is sold, but no money is received. Saga solution, often orchestration-based for control. The e-commerce order fulfillment is a classic candidate for an orchestration saga due to its critical financial implications and the need for tight control over the process. A checkout service receives the customer's request. It validates the request and initiates an order saga orchestrator. Step 1. Create order. The order saga orchestrator sends a command to the order service to create a new order in a pending state. The order service completes its local transaction and notifies the orchestrator. Step 2. Process payment. The orchestrator then sends a command to the payment service to process the customer's payment using an external payment gateway. Success path. If payment is successful, the payment service notifies the orchestrator. Failure path. If payment fails, e.g., insufficient funds, fraudulent card, the payment service notifies the orchestrator of the failure. The orchestrator, upon receiving this failure notification, triggers compensation. It sends a command to the order service to change the order status to canceled. The saga terminates here. Step 3. Deduct inventory. If payment was successful, the orchestrator sends a command to the inventory service to deduct the items. Success path. If inventory is successfully reserved deducted, the inventory service notifies the orchestrator. Failure path. If inventory deduction fails, e.g., item out of stock, the inventory service notifies the orchestrator of the failure. The orchestrator triggers compensation. It sends a command to the payment service to refund payment, compensation for Step 2, and a command to the order service to cancel order compensation for Step 1. The saga terminates. Step 4. Schedule shipping. If inventory was successfully deducted, the orchestrator sends a command to the shipping service to schedule delivery. Step 5. Finalize order. Once shipping is confirmed, the orchestrator tells the order service to set the order status to completed. Benefits demonstrated. High availability. The system remains available even if individual services encounter transient issues, as the Saga orchestrator manages retries and failures. Fault tolerance. Failure in one step, e.g., payment, is isolated and cleanly compensated, preventing data inconsistencies. Ensured business consistency. Despite using independent services, the overall order fulfillment process guarantees that either the order is fully placed and paid for, or it's fully canceled and compensated. External integration seamlessly integrates with external payment gateways, which would be impossible with traditional distributed transactions. Lessons learned. Idempotency is paramount. Payment processing and inventory operations must be idempotent to handle retries without double charges or stock deductions. Managing external dependencies. Building robust error handling and timeouts for calls to external systems is critical. Granular compensation. Each step's compensation needs to be carefully defined and automatically callable. Case Study 2. Travel Booking System. Scenario: a user books a complex travel itinerary, flight, hotel, car rental, as a single logical transaction, possibly across different airline, hotel, and car rental providers. The distributed problem. Each booking, flight, hotel, car, often involves interacting with external, separate reservation systems, APIs of airlines, hotel chains, car rental agencies. These external systems are typically unreliable, prone to delays, timeouts, or transient errors, have their own transaction boundaries, and certainly won't participate in your internal 2PC. If the car rental reservation fails, the already booked flight and hotel must be released to avoid financial loss or customer frustration. Saga solution strongly favors orchestration. Due to the number of external interactions, variable response times, and the high cost of partial failures, orchestration is almost always chosen. A travel booking orchestrator is initiated when a user attempts to book a multi-component trip. Step 1. Book flight. Orchestrator sends a request to the flight reservation service. This service interacts with external airline APIs. Success. Receives flight confirmation. Failure. Flight reservation service reports failure. Orchestrator terminates the Saga. Step 2. Book hotel. If flight is successful, orchestrator sends a request to the hotel booking service. This service interacts with external hotel APIs. Success. Receives hotel confirmation. Failure. Hotel booking service reports failure. Orchestrator triggers compensation, sends a command to flight reservation service to cancel flight. Saga terminates. Step 3. Book car rental. If hotel is successful, orchestrator sends a request to car rental service. This interacts with external car rental APIs. Success. Receives car rental confirmation. Failure. Car rental service reports failure. Orchestrator triggers compensation, sends a command to hotel booking service to cancel hotel and to flight reservation service to cancel flight. Saga terminates. Step 4. Finalize booking. If all components are booked, the orchestrator updates the internal booking status to confirmed. Benefits demonstrated. Handles external system failures. Designed to gracefully manage unpredictable responses from third-party APIs. Maintains composite consistency. Ensures that a user either gets their entire itinerary confirmed or, if a component fails, all previous confirmed parts are properly released. Accommodates long-running processes. Booking external resources can take time, and the orchestrator manages the state across these delays. Lessons learned. Complex compensation. The compensation logic is crucial and can involve cascading cancellations across multiple external systems. Timeouts are essential. External APIs can hang or be slow. Orchestrator timeouts prevent the Saga from getting stuck indefinitely. Human intervention for edge cases. Sometimes compensating an external action isn't possible, e.g., a no-show fee applied by a hotel. There must be a path for human customer support to resolve these exceptions. Case Study 3. Large-scale financial transaction/loan application. Scenario: a customer applies for a loan, which involves multiple departments and external checks: credit scoring, fraud detection, underwriting review, approval, and finally, fund disbursement. Each step involves distinct business logic and often different data stores. The distributed problem: this is a long-running process, human in the loop, with high regulatory compliance requiring an auditable trail. Failures at any stage, even after initial approvals, must trigger controlled reversals or specific reassessment paths, rather than simple technical rollbacks. Saga solution: orchestration for strict control and auditability. A loan application orchestrator acts as a complex workflow engine, possibly integrating with business process management (BPM) tools. Steps: credit check service, external and internal checks. Fraud detection service. Underwriting service, often human review and decision. Approval service. Disbursement service, transferring funds. Compensation: if, for example, the disbursement service encounters a technical issue, e.g., bank system downtime, the orchestrator might trigger a series of compensations. Notify approval service to revert approved status to pending disbursement. Notify underwriting service to flag the application for review for human intervention. Send email alert to relevant support staff. This is not a rollback to an empty state, but a controlled transition to a remediable state. Benefits demonstrated: ensures regulatory compliance, provides an auditable, explicit workflow for critical financial processes, handles human interaction. The orchestrator can pause for human review and resume based on human input. Complex business rules: effectively manages intricate branching logic based on various outcomes, e.g., different types of loans, different credit scores. Controlled state transitions: failure doesn't mean starting from scratch, it means moving to a well-defined recovery state. Lessons learned: auditability is key. Every step and decision in the saga must be logged and traceable for compliance purposes. Designing for human intervention. Sagas can automate much, but complex financial processes often require explicit human gateways and resolution paths. Nuance of compensation. Compensation in financial contexts is often about reversing an effect through a new financial transaction, e.g., clawing back funds, negating a credit line, rather than simply deleting a record. Case Study 4. Supply chain and logistics coordination. Scenario: managing the flow of goods from raw material procurement, manufacturing, warehousing to final delivery, potentially involving numerous internal systems and external partners: suppliers, shippers, customs brokers. The distributed problem. This is a vast, highly distributed, and often long-running process with many potential failure points. Maintaining overall consistency across disparate systems, often integrating with legacy applications, is a constant challenge. Delays or failures in one part of the chain can cascade. Saga solution: often a mix of choreography and orchestration. In large supply chains, a pure choreography approach might handle simpler event chains, e.g., order received event triggers manufacturing request, while critical multi-party processes might use an orchestration saga. Choreography example: raw material ordered event from procurement service triggers inventory service to update expected stock and manufacturing service to adjust production schedules. Component manufactured event from manufacturing service triggers quality control service. Orchestration example: for critical paths with external partners. A shipment orchestrator might coordinate between internal warehouse service, an external customs broker API, and a logistics partner API. Compensation: if a batch of products fails quality control after packaging, but before shipment, compensation might involve notifying all downstream services, adjusting inventory counts, refunding the customer, if prepaid, and potentially re-triggering manufacturing for a replacement batch. Benefits demonstrated: end-to-end visibility, potentially provides a single view of the overall supply chain status. Automates complex workflows, connects disparate systems, and automates the flow of information and goods. Resilience against disruptions, can trigger compensatory actions to mitigate the impact of delays or failures by suppliers or logistics partners. Lessons learned. Integration with legacy and external systems. This often involves significant complexity in translating messages and handling API variations. Long-running eventual consistency. Some sagas might take weeks or months to complete. The system needs to maintain state across these long durations. Coordinating across organizational boundaries. Sagas often cross legal and organizational boundaries, requiring clear contracts and agreements for compensation. Conclusion. These case studies powerfully illustrate the saga pattern's versatility and necessity in modern distributed system design. Whether it's ensuring financial consistency in an e-commerce checkout, coordinating complex external integrations in travel, managing human-centric financial workflows, or orchestrating a global supply chain, sagas provide a robust framework. They underscore that while these solutions introduce architectural complexity, they are often indispensable for building resilient, consistent, and scalable distributed business processes in the real world, addressing challenges that traditional monolithic approaches cannot. Chapter 9, Saga Alternatives and When to Use and Not Use, Sagas. The saga pattern is an incredibly powerful tool for managing consistency across distributed systems, especially those built on microservices. However, like any architectural pattern, it's not a silver bullet. Applying a saga where a simpler solution suffices can introduce unnecessary complexity, leading to overengineering, increased development time, and operational headaches. This chapter explores alternatives to the saga pattern, helping you understand when a saga is the right choice and, crucially, when it is not. Saga alternatives, considering other approaches. Before reaching for a saga, it's essential to evaluate if your consistency problem can be solved by simpler means. 1. Traditional distributed transactions, e.g. 2PCXA. Recap. As discussed in Chapter 2, two-phase commit 2PC offers strong ACID properties across multiple, often homogeneous, participants. When it might be used, in very specific, niche scenarios, homogeneous, controlled environments. All participating data stores are from the same vendor and within a highly controlled network environment, e.g., within a corporate data center with strict network latency guarantees. Absolute immediate consistency is non-negotiable. For certain legacy systems or very specific financial operations where any temporary inconsistency is unacceptable, and the performance scalability penalties are understood and tolerated. Small number of participants. The transaction involves only a few participants, reducing the contention and blocking issues. Why often avoided in microservices? For most modern distributed systems, especially those built on cloud-native principles, the synchronous, blocking nature, tight coupling, and heterogeneity issues of 2PC make it an unsuitable, indeed often impossible, choice. It simply doesn't scale and contradicts the independent nature of microservices. 2. Simple eventual consistency with retries and manual reconciliation. How it works. This is a less formal approach. A service performs an action and publishes an event. Another service attempts to process the event. If it fails due to a transient error, it retries a few times. If it fails persistently, the event might go to a dead letter queue, and reliance is placed on monitoring systems to trigger manual investigation and reconciliation. There is no explicit, automated compensation logic built. When suitable, non-critical operations. For operations where temporary inconsistencies are acceptable and a full automated compensation flow is considered overkill. Examples include updating analytics dashboards, sending non-essential notifications, or user profile updates that can tolerate a slight delay in propagation. Rare failure scenarios. If the probability of failure is extremely low, and the cost of human intervention for those rare cases is less than the overhead of building a full saga. Limitations. Lacks the formal, business-level, undue guarantee of a saga. A protracted or unhandled failure can leave the system in a truly inconsistent state for an extended period, requiring an operator to intervene and manually fix the data. This might be acceptable for some scenarios, but certainly not for core business transactions. 3. Single service responsibility, pushing consistency inward. How it works. This is less an alternative pattern and more a reevaluation of your domain boundaries. Instead of distributing the transaction, consider if the entire logical operation can actually be handled by a single microservice and its own private database. When suitable, poorly defined service boundaries. Often, what initially appears to be a distributed transaction problem is actually a sign that your microservices have been decomposed incorrectly. If two logically tightly coupled pieces of data always need to change together, perhaps they belong within the same service. Cohesive bounded contexts. If all data and business logic necessary for an operation can reside entirely within a single service's bounded context, then a local ACID transaction is inherently sufficient within that service. Importance: this is frequently the best alternative because it eliminates the distributed transaction problem entirely. Always prefer a local transaction if you can. Avoid distributing a transaction if you don't absolutely have to. 4. Idempotent API calls with local retries. How it works. For sequential processes involving just two services or immediate chaining. Service A makes an API call to Service B. If the call fails, Service A retries the call to Service B. Service B's endpoint must be idempotent to handle these retries correctly. When suitable, simple chain calls. For very straightforward, two-step processes where the failure of the second step only impacts its own outcome, and no complex cascading compensation of Service A's actions is required. Synchronous operations. Useful when you need an immediate response from Service B and are comfortable with the blocking nature of the call. Limitations. This approach doesn't scale to multi-step, multi-service workflows. It only handles the immediate, next step, retry, and doesn't provide a mechanism for compensating previous steps in a chain if a later step fails. It is less robust than Sagas for orchestrating complex business processes. When to use Sagas, the sweet spot. The Saga pattern shines in specific scenarios where its benefits outweigh its inherent complexity. You should consider implementing a Saga when your business operation must span multiple distinct services. The core requirement is that a single business transaction, e.g., placing an order, booking a trip, fundamentally involves operations on data owned by different, independent microservices. You cannot consolidate this into a single service without violating good microservice design principles. High availability and scalability demands. You cannot tolerate the locking and blocking behavior of traditional 2PC. Your system needs to remain highly available and process transactions at scale, meaning eventual consistency is acceptable. Complex, multi-step workflows with dependencies. The business process involves a sequence of operations where the failure of a later step necessitates reliably undoing, compensating, the effects of previously completed steps. Simple retries are insufficient. Integration with heterogeneous or external systems. Your business process needs to interact with services using different database technologies or with external third-party APIs, e.g., payment gateways, shipping carriers, external credit bureaus, that you cannot control and that will not participate in an internal distributed transaction. Acceptance of eventual consistency. You understand and accept that the system will temporarily pass through inconsistent states during the Saga's execution, with the guarantee that it will eventually reach a final consistent state, either fully complete or fully compensated. This is a business decision as much as a technical one. When not to use Sagas, avoid over-engineering. Implementing a Saga is a significant architectural decision that introduces considerable complexity. Avoid using Sagas if the operation can be handled by a single service. If a business transaction can be encapsulated within one microservice and its own private database, use a local ACID transaction. This is the simplest and most performant solution. Don't introduce distributed complexity where it's not needed. Strong, immediate global consistency is an absolute, non-negotiable requirement. If you truly need immediate, global ACID transactional guarantees across multiple services without any temporary inconsistencies, and your environment, homogeneous, tightly controlled, allows for it, 2PC might be considered, though still rarely advisable in modern microservices. Sagas embrace ** eventual consistency, not strong immediate consistency. Failures are non-critical or easily manually recoverable if the consequences of a partial failure are minimal, or if manual intervention is a perfectly acceptable and cost-effective recovery strategy for rare occurrences. Simpler eventual consistency models with retries might suffice without the overhead of explicit compensation chains. Compensating actions are undesirable or impossible. If your business operations have no logical undo, e.g., physically mailing a letter, setting off an alarm, or are too costly or complex to compensate, a Saga might not be the right fit. In such cases, these irreversible actions should often be moved to the very end of any business process, after all reversible steps are completed and consolidated. The added development, operational, and debugging complexity is not justified. Sagas are complex to design, implement, test, especially failure paths, and monitor. The architectural overhead must be justified by sufficiently complex distributed consistency requirements. If a simpler pattern can address the core problem, choose the simpler pattern. Complexity versus benefits. The architectural trade-off. The decision to use a Saga should be a deliberate, well-justified architectural choice. It means consciously taking on the complexity of designing clear compensation logic for every step, ensuring idempotency for all actions, rigorous testing of intricate failure and compensation paths, investing in advanced monitoring and tracing tools, correlation IDS, managing potential long-running processes and their state. This added complexity is only worth it if the problem it solves, business consistency across distributed, long-running, or failure-prone transactions, cannot be addressed by simpler, less invasive patterns. Conclusion. The Saga pattern is an indispensable tool in the architect's arsenal for building resilient and scalable distributed systems. However, its power comes with increased complexity. By understanding the alternatives and carefully evaluating your specific consistency requirements, the nature of your business processes, and the implications of embracing distributed complexity, you can make informed decisions. The goal is always to apply the most appropriate solution, not necessarily the most advanced, to achieve reliable and maintainable outcomes. Chapter 10. The Future of Distributed Consistency and the Saga Pattern. As we conclude our exploration of the Saga pattern, it's vital to recognize that the landscape of distributed systems is anything but static. Cloud computing, the relentless adoption of microservices, and evolving architectural paradigms continuously reshape how we build and deploy applications. This final chapter will explore how these trends reinforce the enduring relevance of the Saga pattern, how its implementation continues to evolve, and what key takeaways you should carry forward as you design your own resilient systems. Emerging trends in distributed systems and microservices. The forces driving system design continue to push towards more decoupled, event-driven architectures. Several trends are particularly noteworthy. Serverless computing, functions as a service FaaS. Platforms like Oz Lambda, Azure Functions, and Google Cloud Functions inherently promote breaking down applications into small, independent, stateless units of computation. This model naturally aligns with the principles of Saga choreography. One function, service, completes its work, publishes an event, and triggers another function. The stateless nature of individual functions also pushes the need for external state management for long-running workflows, leading to the rise of durable orchestrators. Durable workflow engines/managed orchestrators. Cloud providers are increasingly offering services specifically designed to manage complex, long-running workflows and state across serverless functions or containers. Examples include AWS Step Functions, Azure Durable Functions, and Google Cloud Workflows. These services essentially provide a managed, highly available, and durable Saga orchestrator, abstracting away much of the state management, retry logic, and error handling boilerplate that one would typically build manually. This significantly reduces the operational complexity of implementing orchestration sagas. Event-driven architectures, EDA, proliferation. The shift toward services communicating via events rather than direct API calls continues unabated. EDAs promote loose coupling, scalability, and resilience. This paradigm inherently embraces eventual consistency, making patterns like Saga even more relevant as the primary means to achieve business-level consistency in such environments. Service mesh, briefly. While not directly implementing Sagas, service mesh technologies, e.g., Istio, Linkerd, provide critical infrastructure for managing communication between services. They offer capabilities like traffic management, advanced routing, robust retries, and comprehensive distributed tracing. For Sagas, these capabilities enhance operational excellence by providing more reliable communication channels and superior observability into the complex web of service interactions. The intersection of serverless and Sagas. The rise of serverless computing is a powerful catalyst for Saga adoption. In choreography Sagas, serverless functions can serve as individual microservices, each reacting to specific events and publishing new ones. The natural event-driven nature of serverless makes this a very lean way to implement choreographed flows. For orchestration Sagas, the durable workflow engines offered by cloud providers are a game changer. They allow you to define your Saga state machine visually or programmatically, and the platform takes care of execution, persistence, timeouts, retries, and error handling. This means developers can focus on the business logic of the Saga rather than the intricate details of building a robust and scalable orchestrator from scratch. This democratizes the ability to implement complex Saga patterns to teams that might not have the resources or expertise to build highly performant, durable orchestrators themselves. Low-code, no-code platforms' impact on Saga implementation. A nascent but growing trend is the emergence of low-code and no-code platforms that allow for the visual definition and execution of business workflows. Many of these platforms are fundamentally building blocks for what effectively become orchestration Sagas. By allowing business analysts or domain experts to define complex processes graphically, these tools can generate the underlying Saga logic, further simplifying the creation and management of sophisticated distributed transactions. This promises to bridge the gap between business intent and technical implementation, making resilient system design more accessible. The enduring relevance of the Saga pattern. Despite technological advancements, the fundamental problem the Saga pattern solves remains: how to maintain consistency for a business process that spans multiple, independent services in a distributed environment. As long as we continue to decompose monolithic applications into microservices, and as long as those microservices own their own data, the challenge of distributed consistency will persist. The Saga pattern is not tied to a specific programming language, database, or cloud provider. It's an architectural pattern, a timeless solution to a persistent problem. Its core principles, local transactions, compensating actions, and embracing eventual consistency, are robust and adaptable. It will continue to be a vital tool in the toolkit of architects and developers building scalable, resilient, and consistent distributed applications. The tools for implementing Sagas will evolve, becoming more powerful and easier to use, but the underlying pattern will remain indispensable. Key takeaways and recommended best practices. To summarize the wisdom gleaned throughout this book, here are essential principles for working with Sagas. Contextualize consistency. Don't blindly aim for global acid. Understand your business's true consistency requirements and accept eventual consistency where appropriate. Design for compensation first. Seriously. Compensation is your distributed rollback. For every step that commits, know exactly how you'll undo its business effect if necessary. Test these paths rigorously. Embrace idempotency universally. Assume messages will be duplicated and operations retried. Design all operations, forward and compensating, to be idempotent. Prioritize observability. You cannot manage what you cannot see. Implement comprehensive logging with correlation IDS, leverage distributed tracing, and monitor key metrics to understand the full lifecycle of your Sagas. Rigorous testing, especially unhappy paths. The complexity of Sagas demands thorough testing. Focus not just on the happy path, but on every possible failure mode and its corresponding compensation. Strategic choice of style. Carefully choose between choreography and orchestration based on the complexity of your Saga, your team structure, and your need for explicit control and observability. For most non-trivial Sagas, orchestration offers significant advantages in maintainability. Leverage reliable messaging and transactional outbox. Use robust message brokers as your communication backbone and implement the transactional outbox pattern to guarantee atomic updates and message emission. Concluding thoughts and future outlook. The journey into distributed systems is one of trade-offs, learning, and continuous adaptation. The Saga pattern, while introducing its own set of complexities, empowers you to build highly available, scalable, and resilient systems that accurately reflect sophisticated business processes. It's a testament to good architectural thinking that a concept from the 1980s has found its ultimate calling in the cloud-native microservices era. As distributed systems continue to evolve, approaches to consistency will become even more refined. Expect more sophisticated managed services, even smarter tooling, and potentially new patterns that build upon the lessons learned from Sagas. But the fundamental understanding of local transactions, eventual consistency, and the crucial role of compensation will remain evergreen. By mastering the Saga pattern, you are not just learning a specific technique. You are deepening your fundamental understanding of building robust solutions in an inherently distributed world. Further reading and resources. To continue your learning journey, explore works by thought leaders in the field of microservices architecture. Delve into the principles of service decomposition, inter-service communication, and data ownership. Event-driven architectures. Understand patterns for asynchronous communication, event modeling, and event stream processing. Distributed systems theory. Explore foundational concepts like the CAP theorem, consensus algorithms, and fault tolerance. Cloud-native design patterns. Learn about how specific cloud platform services, like serverless functions, message queues, and workflow services, can be leveraged to implement distributed patterns. Domain-driven design, DDD. Understand how to effectively model your business domain into cohesive and independent services, which is prerequisite for effective Saga implementation. The world of distributed systems is dynamic and challenging, yet immensely rewarding. The Saga pattern arms you with a powerful approach to tackle one of its most persistent and critical problems, achieving consistency in a truly distributed environment. Go forth and build resilient systems.